We are used to solving this linear equation when one of the variables is given, just like in the event that x is given to be 1, we can right away solve for y by solving this equation. Like we will have something like 21 times 1 plus 12y equals 36. So this would be 21 plus 12y equals 36. And so 12y is equal to 36 minus 21. That's 12y equals 15. And so y is equal to 15 over 12 or 5/4. And so we have solution that is x is equal to 1 and y is equal to 5/4. But what if we are only allowed to have solutions which are integers? And we have to solve simultaneously what x and y are that will satisfy the equation, meaning we don't have a given for either of our x or y here. This would actually lead us to linear Diophantine equation. This theorem right here will be our guide to know if linear Diophantine equation has solutions or not. To picture this out more, let's have this example. Based from our theorem, we have 21 as our A and 12 as our B, with 36 as our C. Notice that in this problem, D is equal to 3 because 3 is the GCD of 21 and 12. Theorem states that if the GCD divides C, then automatically we have integer solutions. And since 3 divides 36, then we are sure that our linear Diophantine equation here has integer solutions. To know more about GCD, just click the gear icon there at the top right corner of your screen. That video as well has a discussion on how come we have these equations right here. So be sure to have that video watched first, alright? So what we have here right now is actually finding the equation that contains the GCD. From the video discussion that we have there, it would be the equation that contains the last non-zero remainder. And yes, that would be 3 in this case as our GCD, knowing that 3 is the last non-zero remainder in these equations. Once we had identified the equation containing the GCD, we just have to manipulate that equation to have something like this. Notice that we just have to equate the rest of the expressions in that equation to 3. For the benefit of others, let's discuss how come we have 9 times -1. Transposing 9 to the other side of the equation will have 12 minus 9. And since -9 is the same thing as 9 times -1, is the same thing as 3 equals 12 plus 9 times -1. Now, as we continue the process in solving the Diophantine equation, we have to equate the rest of the expressions in each equation to each remainder. Just like 3 in this equation, we equated the rest of the expressions with respect to 3. So next would be the remainder 9 in the equation containing 9. So similarly, we'll have 9 equals 21 plus 12 times -1. Once we're done representing all the remainders, the next of the process would be substituting the values that we have at hand. Thus, the first equation will have the substituted value of 9 since we already have a value for 9. After substituting the value of 9, we have to simplify the right side of the equation by distributing -1. Note that we have 12 times 1 because we have -1 times -1, which is +1. And that's the reason why we now have this. This time, let's combine like terms. For the benefit of others, we can actually combine 12 and 12 times 1. This is based from the algebra lesson that factoring out 12 is the same thing as ax plus ay. Factoring out a, we'll have a times the quantity x plus y. Applying this to our 12s here, factoring out 12, we'll have 12 times 1 plus 1, which is 12 times 2. Notice that the left side of our equation is of the format already of 21 times something plus 12 times something as our linear Diophantine equation. But the right side has 36 and we still have only 3. So to make 3 36, we have to multiply the entire equation by 12. And so we have this. But for the benefit of others, let's have this discussion. Since we want to retain the format of 21 times something plus 12 times something, let's base this from an algebra lesson. Notice that after distribution, we can actually rearrange the products that we have right now. Hence, the products AMX plus BCM is the same thing as AXM plus CMB. Relating that to the left side of our equation, when we multiply that by 12, we can just distribute 12 to the negative 1 of 21 times negative 1. That's why we now have 21 times negative 12. Distributing this time 12 to the product of 12 times 2, we can just distribute 12 to that positive 2, having now 12 times 24. Finally, we now have value for x, which is negative 12, and y to be positive 24. Won't believe this worked? Let's check. We have 21 times negative 12 plus 12 times positive 24, and there you go, the answer is 36. We have a bit shorter way of answering this. Just click on the gear icon there, the top right corner of your screen, and you will be redirected to that video. Now, this example will be for those equations which have more than 2 remainders to consider. Our previous example only had 2 remainders to consider. That was the 9 and 3. Unlike in this example that we have another remainder to consider, which is 676. As discussed, we have to equate the rest of the expressions in that equation containing 676. And so we have 676 equals 8,216 plus 158 times a negative 5. As noted, the rest of the process would be this. Having a value for 156, we can just substitute that to the 156 that we have at the first equation. And after the substitution, we just have to distribute that negative 4 and we'll have 676 plus 158 times negative 4 plus 676 times a positive 8. That becomes positive 8 because we have negative 2 times a negative 4. And we prefer that because we want to retain the 676. And so now, combining 676, we have 676 times 9, and that is because, again, from an algebra lesson of factoring out 676. Now, we have there 1 and 8, so that becomes 676 times 1 plus 8, which is 9. Now, this is what happens if we have 2 remainders to consider. Notice that we still have 676. And so we still have to continue with the process, that is substituting 676 to the next line. And the same process continues. That is, after substituting, we just have to distribute 9. And so we have this. Again, we have that negative 45 there because we want to retain 1,508, and so that would be 9 times negative 5, which is negative 45. So same thing, next would be combining 1,508, and so we have 1,508, which would be negative 49. And yes, that's negative 49 based on the algebra lesson that we discussed at the right side of your screen. And so if the given linear Diophantine equation would be something like 8,216x plus 1,508y equals 52, then our x would be positive 9 and y would be negative 49. Won't believe again? Then let's check.